Welcome to the 13th video in the Beginning Artificial Intelligence series, and in this video we are going to look at reinforcement learning. We have already covered supervised learning with image classification, unsupervised learning with autoencoders and GANs, and now we are going to get into reinforcement learning. Reinforcement learning involves an environment where an agent can act based on sensory information or states that the agent gets from the environment. We can look at an image that kind of reveals how this looks. We have an agent right here that has an action that affects the environment, and then we have an interpreter, which is in my module will actually be part of the environment, and the interpreter will give the reward to the agent, and it will also give the state to the agent. Okay, so now we're going to actually look at the module real quick that's offered from PAI-Utils. We're going to see just a couple things that we can do with it, what it offers, and then in the next video we will actually use it for some real examples. Okay, so the first thing we have is we have environment right here. Environment is pretty much a class that you'll use to inherit other classes. You can see right here we have the gem wrapper, and this is for OpenAI gems. And so if you make your own, you can inherit from environment, and you just have to fill out these. You don't have to fill out the play episode and play episodes, but you'll have to fill out everything else, and then you can just inherit these and you can use them. Alright, so you can also look, the gem wrapper looks pretty much the same. It just inherits those play episodes. And then we also have this environment right here. This environment will actually allow multiple agents to compete against each other in a sequential manner, meaning you can have two agents, and one agent will go and another agent will go, and then it will repeat that. And you can see how you can also shuffle it. That's an option for the play episode right here. And you can shuffle it so that the first agent doesn't always go the first time in a game. And then we have a couple policies right here. Policies are used to select an action or change an action. So you can see right here, this is the greedy policy. This just selects the max, gives you the index of the max value in the action function. So this will be used for agents that give you a high value, and the higher value the better the action. So then you can use greedy. This one is pretty much the opposite. This will just allow you to select the lowest. You can see how we have the min, not a max there. And then we have the stochastic policy right here. The stochastic policy will actually allow the policy to be a little random. It will, if we look at it right here, there's a chance right here that will just select a random integer instead of actually using what the agent actually would want you to select. And this stochastic policy actually inherits or takes another policy as a parameter. So you would actually give it, let's say, the greedy policy, and then it would use that greedy policy when it's not being stochastic. We also have a noise policy. This is for actions that aren't discrete, like these actions. All these are for discrete actions. The noise right here, and the uniform noise and temporal noise, those are all for continuous action spaces. So these will just add numbers, values to the predictions of the actions. So you can see right here, we have the action function, we call that action function, and we just add noise to that action. Now we have a couple decays. Now the decays right here are all used by anything that needs a value to potentially go down. So you can see the noise policy right here has a noise scale decay training. So you can use one of those decays, and you can see that the noise scale right here will actually decrease. We can decrease it with a decay. And for the stochastic policy, we also can decrease it. Every time you call this, it will actually decrease it. You can see we pass it right there. And then we also have a testing one in both of these that is just for some noise to add when you're actually running the test. Now, you don't always want that, but for some agents, you may want some more randomness than you get with the normal agent. Okay, so you can see we have a constant decay here, an exponential decay, and then just a linear decay. Now we have a couple memories right here. These are just for holding values. It's pretty much just a Python list, this one. You can see right there in the comments. And the ring memory is just a DQ. Okay, so now we can look at the playing data. Alright, so the playing data you won't use much. It's more behind the scenes. You will set it in your agents, but playing data is used when we actually go into the environment play episodes, you can see that we kind of use it here. Let's expand this one. You can see how we're accessing. Is it training? Is this agent training, or is it just exploring? So you can go see right now, if we go to the actual playing data, you can see you give it training. It's a Boolean. Do you want to train? Memorizing, it's a Boolean. Do you want to memorize? Epochs, how many epochs it trained per episode, and learns in episode. So if that's true, that's how many. But if you had epochs to, like, let's say 3, and then you had learns an episode to true, you would actually, every single step in the environment, not an episode, but a step in the episode, you would actually train 3 epochs. And then you have the learning parameters, which just match whatever the agent takes for its learning function. Now we can look at a basic agent. This is just a random agent. It doesn't actually use memory. All its actions are just random. If we expand this, you can see it's just random. Now we can look at the Q agent. The Q agent is a Q table. It's a Q learning agent, and it uses a Q table to keep track of the Q values. And so Q values are pretty much how good an action is with account to future rewards. So it predicts, based on this current action, if I take this action, how good is this action? And it's taking into account how good actions after it, or what rewards you can get in the future. And that's controlled by the discount rate right here. So the higher the value, the more you care about the future rewards, and the lower, the less. And you can see this agent, it doesn't use a memory instance. It only has short-term memory. It's just the current step, and that's it. And you can see the main algorithm for doing this is you just have this right here. So it takes from the states, the action, from the states and the action, and this is pretty much how it learns. So that's if you wanted to implement it yourself, that's pretty much the meat of the Q agent. All right, now we can look at a PQ agent. It's just pretty much a parallel Q agent. It just allows you to have multiple discount rates and learning rates, and it lets you, in a way, hijack one agent with a certain discount rate, whichever is the first discount rate and whatever is the first learning rate. That will be the main agent, and all the other agents, or all the other Q tables that have different discounted rates and learning rates, will just be trained off that agent. So it can help you explore a bunch of different parameters in a quick manner. Okay, now this is one of the more advanced algorithms. It's a DQN agent, and it uses a neural network to actually predict Q values. So the Q table, the problem with these Q agents and PQ agents is that they have a Q table that you just can't, it's all discrete. You can only have so many, and so let's say we wanted to have the state be an image. There's way too many different values, discrete state spaces, so that's why we have to use a neural network to predict it, to estimate it. So you can see when we create it, we pass a Q model, which is just going to be a Kira's model, neural network model. Okay, and you can see we have a couple parameters here. We have enable target, enable double, enable per, and these just allow you to enable different features of a DQN. So enable target will just allow you to have an extra target. DQNs can be unstable, so by having an extra target, you pretty much have another model that you're using to train. We can look actually in the train step right here. You can see the code right here. So let me expand this all. You can see we're using a target Q model here, or a double. If we're using a double, we use the Q model, and then we use the target Q model. So the Q model just doesn't update as frequently as the actual Q model, and this will allow it to be more stable. Then we also have this right here, prioritized experience replay, and this is implemented a little differently than in normal implementations, but it does seem to work sort of. It's probably not the best compared to the real implementations, but the other implementations seem to slow down a little bit. And so you can see how I just added, it's pretty much just a little addition to do this. If we can expand all this real quick and see, we have a per loss and we have this one. So you can see if we're not using per loss, all we're doing is we're just random sampling. And if we are using the per loss or the prioritized experience replay, you can see we just pass it right here. So these are just probabilities. So this is why it's different. Normally you just select the ones with the highest loss, and that's the prioritized experience replay, but we give it a probability with the loss. So this is the absolute loss of the actions and or of the Q values, and you can see we just use that as probability. So it's a little different implementation, but it does allow you to do other memories that have a low loss, but they might have changed, so that you aren't eliminating those experiences. You just lower the chances of choosing them. Okay, so that's pretty much everything for the DQN agent. In the next video, we'll definitely show an example of that agent. Now we have a PG agent. That's a policy gradient agent, and that's trained with policy gradients. A PG agent is an actor. So the DQN agent was a critic, and that means the critic will actually rate actions. A PG agent or an actor will actually select actions. So with a DQN agent, we can treat it like an actor by selecting the highest rating, and that can give us an action. But a PG agent and other agents that we'll look at in a second, they mainly just choose an action. Okay, so we can see there's a couple parameters here. We don't need a policy like the DQN agent. PG agents and other agents that inherit from PG agent, they do not need a policy, and actually the others will not allow you to give it a policy because they explore with how they predict their actions. So if we expand all this, you can see that we actually do a random choice and we give it the probability. So this, you have to, when you pass the actor model, you have to give that a softmax so that it outputs probabilities, because this can't sum more than 1, and it has to be exactly 1 in the actions, or it will give you an error. And then we can now look at the DDPG agent. This is a deep deterministic policy gradient agent. This agent does not seem to quite work, so I have a little warning here. You can try it out, but I haven't been successful with it. It may just be hyperparameter tuning, but I am pretty sure there might be a bug. And I've looked through this pretty thoroughly, so if any of you know and understand a deep deterministic policy gradient agent, definitely look at it, and you could definitely message me on Discord if you find a bug, or just on GitHub, which we can look at real quick right here. So the PAI-Utils has been officially released now, so you can download it right here with that command, or you can actually go to GitHub and clone it, and you can see if we look at PAI-Utils right here, you can look at all the code, and right now we're looking at the reinforcement. So you could look at this and you could bring up an issue, and you could tell me how to fix it if you find a bug. Okay, so that is it for this module. We also have another module that gives us a couple other agents. We have the DQN PG agent. This is just a combination of a PG agent and a DQN agent. It pretty much allows you to hijack a deep Q network and allow the deep Q network to explore and to exploit, but the PG agent is using the memory that the DQN agent gets to train itself. So this will allow you to, with one agent, kind of train two agents and see, hey, maybe like one example use case of this would be sometimes a PG agent just cannot do a certain task, and so you could kind of train the PG agent by piggybacking on the DQN agent, and then you could train an actual PG agent. Now this is one of the best agents right here. This is the Advantage Actor Critic. An Advantage Actor Critic uses pretty much a DQN-like structure and a policy gradient-like structure, because they're actors and a critic, and you use that to calculate the advantage. So all these others were pretty much calculating the Q values or discounted rewards, which take into account how good a future, an action is based on its current reward and some discounted rate of the future rewards. But Advantage allows you to do that, but also, hey, what else other actions are there that I can take at this current state? Oh, for example, if one action in the current state you're in gives you 5 points, which is good, you want 5 points, or another action gives you 10, the advantage of that one action would be 5, and the other action would be 0. So it kind of allows you just to look at the advantage of taking an action, and it doesn't only look at the discounted reward. So this allows you to do some pretty good things. Like I said, it mixes a PG agent and a DQN agent, and it performs pretty well. Now we have a PPO agent. This is another implementation that does have a warning when you use it. I've tested it and it does work. It does work, but it is not as good as the Advantage Actor Critic, and it's not even as good as the PG agent. So I'm assuming there is some sort of bug. And again, if you understand a PPO agent, proximal policy optimization agent, then definitely take a look at my code. And if you could find a bug, I'd be much appreciated. Okay, now we also have two other agents here. This agent is not yet implemented. Eventually it will be implemented, maybe not in the near future though. And it will allow you to have a PG agent, but for continuous action spaces. And the name may change, and this actually may be implemented just in the PG agent by itself, and it may just be a boolean that you can choose continuous action or discrete action spaces. Now we have the last agent here. This is a twin delay DDPG agent, and this agent has another warning. It inherits from DDPG, so it doesn't have a warning explicitly in here, but because it uses a DDPG, it does warn that the implementation may be incorrect. So again, if you find a bug in the DDPG agent or in this agent, it would be much appreciated. Okay, so that is everything for this video. We have gone over these two modules. In the next video, we are going to look at some real examples of using reinforcement learning. Goodbye.